Hello, welcome to another lesson about the Hamilton-Jacobi formalism. Today we are going to look to two special cases that can be presented when solving this differential equation with respect to a mechanical system. And we are going to use an example that we have been watching in recent lessons, which is the one that studies a particle in a uniform gravitational field. We have been working with Hamiltonians of the form H that depends on Qi, Pi, and T, and we know that this corresponds to a Hamilton-Jacobi equation of the form H of Qi, comma, the partial of S with respect to Pi, the time, and then plus the partial of S with respect to time equals to 0. You can notice here that we are introducing a function S that we have been talking about, that this represents a canonical transformation. So that means that, we can find some new functions that are generated from S that relate some new canonical coordinates with the original coordinates that are Q and P. Okay, we have been working with a function S that actually satisfies these two equations. Pi equals the partial of S with respect to Qi, and Qi, upper Qi, is equal to the partial of S with respect to upper Pi. Okay, when you know that Qi is a function of Qi, Pi, and that Pi is a function again of Qi and Pi. Well, in this case, we are going to see what happens if we consider a new canonical transformation that will be very similar to this, but it will have a very important difference. You know that actually we have that there are four generating functions for canonical transformations. One is the one that satisfies these two equations, but we can have, for example, another one that is that Qi equals negative the partial of S with respect to Pi, and Qi equals the partial of S with respect to Pi. Notice that in this one we were calculating the conjugate momentas, and now we are calculating the generalized coordinates Q. Okay? So we are going to consider that our new generating function S satisfies these two equations to see that, the Hamilton-Jacobi equation is going to take a different form. The Hamilton-Jacobi equation for this generating function will be H, but now we know that we should write Qi here, but we are going to write minus the partial of S with respect to Pi, and then Pi, the time, plus the partial of S with respect to time equals to 0. Notice the difference with this equation. Now, instead of substituting the Pi with the derivative of S, we are substituting the Qi. Perfect. So getting back to the example of the particle in the uniform gravitational field, we know that the Hamiltonian for that example is that H is equal to px squared plus py squared divided by 2m, and then plus mgy. So in this case we can identify the q as the y that is here, and we should construct the Hamilton-Jacobi equation for this Hamiltonian as follows. It will be a px squared plus py squared divided by 2m plus mgy. But according to these differential equations, we know that y should be equal to negative the partial of S with respect to Py, according to this equation. So that means that here we need to write minus and then the partial of S with respect to Y here, and then plus the partial of S with respect to time equals to 0. Okay, another important thing that we have been working with is that if we look to our Hamilton function, the Hamiltonian function here, we know that it doesn't depend on the t. Okay, so when we construct a function S using, well, this equation here, S equals W of Px and Py plus a function of t. We know that this function t can be, well, this function of t can be a linear function. So we are going to say that this is going to be equal to a constant times t, and let me write this as minus p1t. Okay, again, we can write this linear function of t because the Hamiltonian does not depend explicitly on t. Okay, and this w is a function of px and py. We do not know what is the form of w yet, but we are going to find it by taking this s into the Hamilton-Jacobi equation. So what are we going to get? Well, we know that we need to calculate the partial of s with respect to time and the partial of s with respect to py. So the partial of s with respect to py is going to be, of course, the partial of s with respect, the partial of w with respect to py, and the partial of s with respect to time is obviously minus p1. So what happens if we take these results into the Hamilton-Jacobi equation? We will get px squared plus py squared divided by 2m minus mg, the partial of w with respect to py, minus p1 equals to 0. Perfect. So with this, we know that, well, we have a derivative of a function with respect to only one variable. So we can solve this differential equation very easy. So from here we can easily see that the partial of w with respect to py is going to be equal to minus p1 divided by mg plus px squared plus py squared divided by 2m squared g. Okay, and we can easily calculate a w in terms of py and px by taking this differential to the right hand side and then taking the integral. We will get that w is equal to minus p1 py mg plus px squared py divided by 2m squared g, and then plus py to the third power divided by 6m squared g. And then we need to add a function of p of x, of course, because remember that w is a function of py and px. Actually, this is px py, right? So we are just taking here the partial derivative with respect to py. So when we calculate that with this w that we have here, we will get that, well, we are going to get this because this function does not depend on py. So the derivative with respect to py will be equal to 0. So we need to add this function to have a complete form for w. Perfect. So remember that we proposed that the function s was going to be the sum of w minus p1t. So that means that we can write that s is going to be, well, all these elements that we have here, and then minus p1t. Perfect. And, well, it is not very hard to notice that if we propose f of p of x equals to p2 px, well, we will satisfy the Hamilton-Jacobi equation with this function s. So that means that the complete solution for the Hamilton-Jacobi equation will be this one over here. Okay, perfect. So this is the s that we wanted to find. Perfect. Okay, perfect. And if we remember the equations that define the generating function s, well, we know that qi is equal to negative the partial of s with respect to pi, and that qi is equal to the partial of s with respect to pi. So from this we can say that x is equal to negative the partial of s with respect to px, and y is equal to negative the partial of s with respect to py. Okay, so we can see that x is equal to minus the partial of s with respect to px, and that is going to be minus px py divided by m squared g, and then plus p2. Actually minus, right? And then y is going to be the partial of s with respect to py. That is going to be p1 divided by mg, and then minus px squared divided by 2m squared g, and then minus, it will be py squared divided by 2m squared g. Okay, with this we can write that this is p1 divided by mg minus px squared plus py squared divided by 2m squared g. On the other hand, we know that q1 is going to be the partial of s with respect to p1, and if we calculate that, we are going to get that this is minus py divided by mg minus t, and q2 is equal to px actually. So yeah, q2 is equal to the partial of s with respect to p2, but that is px. So with this we have found what is q1, what is q2, but we still need to find p1 and p2. But from these two equations we can immediately see that p2 is equal to x plus px py divided by m squared g. So here we have p2, and then p1 is equal to px squared plus py squared divided by 2m squared g, and then plus y, and then this all multiplies mg. So we get that p1 is equal to px squared plus py squared divided by 2m like this, and plus mgy, which is identified as the Hamiltonian. As we have seen in other examples, when we find p1, it turns out to be equal to the Hamiltonian, but well, that is because in this example, well, the Hamiltonian is equal to the total energy of the system, so that is a constant of motion. Again, recall that all these variables, upper variables, well, they are constants of motion because we are working with a generating function of a canonical transformation that is related to a new Hamiltonian, k, that we know, that is equal to 0. Okay, so if we follow the Hamilton equations, we know that qi dot is equal to the partial of that new Hamiltonian with respect to pi, but if k is equal to 0, that means that qi dot is equal to 0, giving us that qi is a constant. And the same thing happens with the pi, because the pi dot is equal to negative the partial of k with respect to qi. And these two equations, remember that they hold because a canonical transformation needs to hold the Hamilton equations. Okay, so with these results that we have here, we have found those canonical transformations, q1, q2, p2, and p1 in terms of the original coordinates q and p, the little ones, right? So, okay, perfect. So right now we are going to look to another example to solve the Hamilton-Jacobi equation given a Hamiltonian function, to see when the method of separation of variables fail. Okay, actually something you can notice from this function s is that it is not separable. I mean, it cannot be represented as the sum of the product of two functions of one variable. So this s was not able to be found with the method of separation of variables. So we are going to look to another example of a Hamiltonian that its Hamilton-Jacobi equation cannot be solved with that method, but we are going to construct a new equation with a change of variable that is going to be solvable with the method of separation of variables. So we are going to say that we have a Hamiltonian equals to p squared divided by 2m minus kt cubed. Okay, first of all, well, recall that this is the element that corresponds to the potential energy. So we know that a force F can be expressed as minus the derivative of the potential with respect to some coordinate. So if we have that our potential is minus KTQ, well, we can see that the force F is equal to minus the derivative with respect to Q of this, but that is going to be minus KT, so that is KT. Okay, the thing here is that we can see that this Hamiltonian corresponds to a particle that is under the influence of a force that has this form over here, okay? I mean, there is a force acting on that particle that is proportional to the time, and here K is of course a constant. Okay, and this term obviously corresponds to its kinetic energy. Okay, perfect. So with this, we are going to use again the function S, generating function, that corresponds to the equations Pi equals to the partial of S with respect to Qi, which is the equation that we have been using in the most examples in the channel, and Qi equals the partial of S with respect to upper Pi. Okay, so this is of course for a Hamiltonian of the form Qi, Pi, and T. So the corresponding Hamilton-Jacobi equation will have the form the partial of S with respect to Q squared divided by 2m, and then minus KTQ plus the partial of S with respect to time equals to 0. Okay, so the element that is guilty for us not to be able to use the method of separation of variables is this element here, because we are multiplicating the t and the q. Okay, but there is something we can do. First of all, notice that we can rewrite this as, well, just for these two elements we will have that, for example, the derivative with respect to time of S minus k qt squared divided by 2 is equal to actually the same thing that we have here, right? Because if we take the derivative with respect to time of S, we get this element, and the derivative with respect to time of this, we get this, what we have here. So we can rewrite the Hamilton-Jacobi equation as 1 divided by 2m, the partial of S with respect to Q squared, and then plus the partial with respect to time of S minus KQT squared divided by 2 equals to 0. Okay, so here comes the trick. We are going to introduce a new function that is going to be equal to what we have here inside. Okay, so that will make the Hamilton-Jacobi equation to have an element that is going to be the derivative with respect to time of that new variable, let's say S tilde. And the Hamilton-Jacobi equation has always this element, the partial of a function with respect to time alone. So that is what we are going to get with that. If we name this as this new function, we will get an element alone as this, what I just wrote here. I mean, the partial of S tilde with respect to time is going to be this element here. So we are constructing a new Hamilton-Jacobi equation. And the thing here is that when we take this element S, well, it can be expressed as, it will be S tilde plus KQT squared divided by 2 equals to S. Okay, so here's the important thing. When we take this S into this part of the equation, notice that we are taking the derivative with respect to Q. So that is going to make this Q to disappear. Okay, so this derivative will be only a function S tilde and then KT squared divided by 2. So this Q will no longer be here in this expression. Let me do it for you to see it more clear. We are going to have 1 divided by 2m, the partial with respect to Q of S tilde plus KQT squared divided by 2. And this all is raised to the second power. And then plus the partial with respect to time of S tilde, and this is equal to 0. So here we are going to take the derivative of each element that we have here. So we will get that the derivative of S tilde with respect to Q plus the derivative with respect to Q of all this, but that is going to be kt squared divided by 2, and this is raised to the second power. Like I mentioned, here the Q has disappeared. And then plus the partial of S tilde with respect to time equals to 0. Okay, perfect. So with this we have constructed the Hamilton-Jacobi equation, and well, we see that it doesn't include explicitly a Q. So that means that the proposal that we are going to do to find the solution for this differential equation is going to be, well, of the form S equals to a function of the time plus a linear function on Q. Let me say that the constant here will be named as P. Okay, and why is this? Remember, the piece of the function that depends on the Q will be a linear function, looking that the Q does not appear in the Hamilton-Jacobi equation. Okay, so right now we were able to use the method of separation of variables into the Hamilton-Jacobi equation, because with the change of variable we did, and this is still the right, with the change of variable we did, now it is possible. So we will get that, let's say, that the derivative of S tilde with respect to Q is equal to P, and of course the derivative of S tilde with respect to time is equal to, well, the total derivative of S with respect to time, right? Because only F depends on the time. So that means that we can rewrite the Hamilton-Jacobi equation as 1 divided by 2m times P plus k t squared divided by 2 squared plus the derivative of F with respect to time. And this is equal to 0. Okay, perfect. So with this we have a very easy differential equation to solve, because, well, we can see that this can be seen as minus dt divided by 2m p, let's say, p squared plus pkt squared plus k squared t to the fourth divided by 4, and this is equal to df. So with integration we can find what is f. So we will get that this is minus the integral of dt divided by 2m p squared plus pkt squared plus k squared t to the fourth divided by 4. So we will get that this is minus, let's say, p squared t divided by 2m minus pk t to the third power divided by 6m, and then minus k squared divided by 40, and then t to the fifth power, yeah, like this. And here we have an m, right? So we propose that S is F plus PQ, and that S tilde is equal to S minus KT squared Q divided by 2. So S is equal to S tilde plus KT squared Q divided by 2. So this takes us to have an S equals to PQ, and then minus 1 divided by 2m p squared t plus pk t to the third power divided by 3, and then plus k squared t to the fifth power, and then multiplies here at 20 like this. And then we sum kt squared q divided by 2. Okay, perfect. So with this we have found a function S that is the solution of the Hamilton-Jacobi equation corresponding to this Hamiltonian over here. So perfect. With this we are able to find the equations of motion of the system, because remember that we have that Pi is equal to the partial of S with respect to Qi, So this takes us to have that P is equal to the partial of S with respect to Q. And well, we can easily see that P is equal to upper P plus kt squared divided by 2, just by taking the derivative with respect to Q of this. So we have this first result. And recall that this P is depending on P, which is a constant, and the time. So this is like one of the solutions of the Hamilton equations already. And if we use the second equation for this generating function S, which is Qi equals the partial of S with respect to upper Pi, this means that Q, let's say Q, yeah, just Q, right, is equal to the partial of S with respect to P. So what are we going to get if we do that? Well, Q is going to be Q and then minus Pt divided by M and then minus kt to the third power divided by 6m, right? Just by taking the derivative with respect to P, this upper P of S. So with this, we can find easily that little q is going to be, well, as a function of time, right, is going to be q plus pt divided by m plus kt to the third power divided by 6m. Remember that q and p are constants, so this is telling us what is the solution to the equation of motion of the system, because it is the coordinate q in terms of the time. So yeah, that is the full solution of the problem. Perfect. So with this, we have finished the lesson. So I hope you enjoyed this video. And I think I will finish here with these two examples.